So it's my great pleasure to be here all the way from New Zealand. Thank you very much for the organisation of what has proved to be a really wonderful and rich conference. So I'm going to talk today a little bit, for those of you that know me, about a topic which I'm quite passionate about, which I'll start with a little story, quite how I got here. Now, for those of you that have kept up with my work over the last few years, know that if there's anything that excites me more, it's a numerical table in Sanskrit sources. So quite often I find myself in manuscript libraries or looking at PDF copies, rifling through manuscripts and looking for tables. Luckily, of course, tables, like diagrams, are quite easy to spot in manuscripts, unlike a sort of an obscure theory that's expressed in Sanskrit where you really have to work hard to find what you're looking for. So I start with this unnamed manuscript. I'll tell you a little bit more about it in a minute, from the National Archives in Nepal, which is an incredibly well looked after manuscript collection because it's done in conjunction with German research agencies. And lo and behold, after looking through this manuscript, which I was working on with a PhD student of mine who I'm jointly supervising with, or was jointly supervising with Professor Kim Plofka, I found a table and a very, very big long manuscript here. And of course, the first thing I do is to grab the table, this is a little bit, and get the whole table in its entirety. Now, of course, we're used to looking at numbers. They're usually to do with administrative documents, and we don't find very much joy in them. But of course, this one's in Sanskrit, and it's several centuries old, so much more exciting. So the first thing you can do when you find a table is just have a look at the numbers. Now, there are a few things that are a little bit different about tables that generally get expressed in Sanskrit manuscripts. And that is, while we're used to, say, an Excel spreadsheet in which our argument generally runs downwards down the page, we have here an argument which runs just along the top here. So you can see, if you can make it out, I'm sorry it's a little bit small, I wanted to get the whole thing for you. We can see we go, start up here, counting in Nagari numerals, should be familiar to most of you, 1, 2, 3, 4, it's a little smudgy, this manuscript, 5, 6, 7, 8, 9, 10, and so forth and so on. We get up to 30 at the end, we slip down. Okay, so it's in a sense this table is 3 stacks of rows, 31, 32, all the way along to 60, and then on the next folio, which is why this is sort of hanging around of the manuscript, we go all the way up to 90. So getting a little bit of a feel for the table before we look at exactly what it is a table of, we see that this has 90 entries. That gives us a little bit of a clue what mathematical function might be tabulated here. Other few things we can look at when we're looking at sort of massaging or at least getting a feel for the data, just have a look at some of the entries. Now, the entries that are associated with each argument in the table, again, are expressed a little differently to how you might be used to. Rather than being read horizontally across the page, which we're used to reading numbers, these instead hang down in the argument. So you really read these. So the number that's associated with the first argument hangs down on the page like this, okay? So we read it, and again, it's a little smudgy, 1, 2, 49, 43, 11, if you can make that out. So it's a number with lots of what I will tell you are sexagesimal places, or it's a number with a long string bits on it. Okay, so we can see if we look at the data in a very general sense, we can see the first entry is 1 with a lot of numbers after it, the next one is 2 with some numbers after it, 3, 4. So we can see actually if we looked through these a little more carefully, it's increasing monotonically all the way up to 60, which is our number at 90 degrees. A very nice 60 with lots of zeros after it. Other things we can tell about the table, and some of you might be getting an idea of what this might be a table of. It's got 90 degrees, it's a very famous mathematical function, it's something India can be justly proud of. Another key feature that I'm looking for, I have a hunch of what it is. If I look at this value for 30, I see the value for 30 is itself 30, okay, which is half of this value of 60. So, because I've seen quite a few of these tables, my hunch was correct, and indeed this is a table of signs, okay? The nice little familiar thing that we know about sines, of course, is that the sine of 30 is half of this radius, or this amount here, which confirms that it's indeed a table of sines. So having a hunch of that this was a table of sines, and a very precise one, in that we ask ourselves the question, who wrote this table of sines? Who used this table, and how did they compute it? All right. So, what is this table from? It's from a manuscript of a wonderful Siddhanta, a monumental work called the Sarvasiddhantaraja by a scholar called Nityananda, who was in fact an astronomer at the court of Shah Jahan, working in the first half of the 17th century. We don't know very much about the biographical details of the situation of what he works, but as more research is uncovered about the situation of scholars at the Mughal court, we will learn more. He's well known, though, for his tabular works, although the Sarvasiddhantaraja is not a tabular work. The table that I showed you is the only one that's included in the manuscript. So we've got two other works that he's noted for, which are tables, and one is called the Amrita Lahari, just looking at tables because they're just so pretty, which is a work which helps make panchangas for various different cultures, so it's a very interesting work, quite short, only 50 pages long. And the other one, in contrast, the Siddhanta Sindhu, is this enormous set of numerical tables, which all you can see up there, of course, is a blur of little tiny black digits, which nobody can possibly read. This is the only copy of it, and it's actually not a terribly good photograph of it. This is but one page of 800 pages of numerical tables. Now, quite aside from the fact that somebody is computing every single one of these numbers, is the fact that somebody sat down and copied every single one of these numbers as well. Not only that, of course, the daunting task for the historian is what to do with this massive work. Do we start transcribing all of these into Excel? Sorry, is this a little bit... Is it okay to listen to? Or how do we start by even... recomputing the data itself. Okay, the Siddhanta Sindhu itself is quite interesting. It gives us a little bit of perspective on the conditions or some of the priorities that Nityananda was working under. In fact, the Siddhanta Sindhu is loosely what we might call a translation of a work which we find in Persian called the Ziji Shah Jahani. The translation was composed by Asaf Khan, who was the father-in-law of Shah Jahan himself. The Persian translation, the Persian work, in fact, is a recasting of an original Arabic work. So this Siddhanta Sindhu is, in fact, a Sanskrit translation of a Persian translation of an original Arabic work. It's very interesting things when you look at the transmission of tables through various cultures. But going back to this sine table, so we want to ask ourselves the question, how did Nityananda compute it? How does the text that we see around the table support the numbers that we find in there, and how is it supposed to be used? And in what context was it supposed to be used? Well, lucky for us, in the Siddhanta Sindhu, Nityananda is very, very adamant that anybody who calls themselves a mathematician or an astronomer should really understand the rationales. Many astronomers make this claim but spend very little time dedicated to the demonstration or proving or validating the results in question. So one of the famous verses that in fact is in the Gola section of Siddhanta Sindhu is this lovely verse here which goes, Yat kinchit ganitam grahasya ganako janam vinavasana Prishta sana parena gola vidusha prashna prapanchoktibihi, and it keeps going like this. A mathematician, he says, knowing some mathematics concerning planets without knowing the rationale was questioned by another person who was an expert in spherics. What could he say as an answer to those questions, being ignorant in the science of the spheres? Because of this, he says, I will state a pleasing composition on the investigation of the spheres for the delight of all being. Now, this is in the context of the Gola, which is slightly different from the trigonometry section, but Nityananda reinforces this idea. You absolutely have to know what's going on before you can use this and call yourself an expert. But not only does he say it, but he really demonstrates it by his coverage of the treatment of various topics in his Siddhanta. So we look around, we're looking to try and answer the question, where did these values come from? How did Nityananda compute a sine table? So we look around in the manuscript, in the passage around the sine table, and we see a lot of verses, in fact 60 verses, around 60 verses in all he dedicates to trigonometry. But we also see some very pretty diagrams here, and we also see some more diagrams here, and we also see some constructions. Now, for those of you who have seen a little bit about Sanskrit diagrams, will notice some of the interesting features of these diagrams, like we saw in Professor Plofker's talk on Monday, the addition of these lettered points here on these diagrams, which is a relatively new feature. Not only do we see diagram in a lot of verses, but we also see these little wee identities here. For those of you who can read some Devanagari, this is Yava 1, Yabu 1, and we saw in some cases about the use of algebraic or symbolic styles of reasoning, this is shorthand algebra, to work through mathematical identities. So we see verses, diagrams, constructions, and what appears to be algebra in this passage surrounding this sine table. So where does the sine table appear in the greater context? In fact, the Sarvasiddhantaraja has 9 chapters in the first Ganita section of the work. Sines occur in Chapter 3, just before true positions of planets are to be dealt with. That is because in order to find these orbital corrections that you need to convert from mean positions to true positions, you need trigonometry to do so. And it's a huge portion of this work, some 65 verses, as I alluded to. So it's right smack bang in the middle of the heart of astronomy, computing planetary longitudes and velocities. The section itself is quite long, and what we're going to do is we're going to scoot through it relatively quickly, dwelling on just a couple of the very interesting formula that he gives and the rationales he gives behind some of them, to look behind how the data that we find in this sine table was computed. So he starts with the opening verse, Acharya Varya Ganakastaeva Janantiye Janayayo Papatim. So, O revered teachers, only those are considered mathematicians who know the rationale behind the computation of the sine. So here we go, the importance of this rationale or this demonstration. Therefore, he says, by venturing to explain that, even a dullard like me, oh come on Nityananda, really, wishes to accomplish their status. So the idea is, in order to really understand what's going on, to be considered a mathematician, a Ganika here, you really need to understand how to compute the sines and not just to use them. Now, if Nityananda is calling himself a dullard, and in fact it's a lovely term here, this Mahajado here, a very big dullard, a very big, thick person, we'll just remind ourselves a little bit about some of the geometry behind the trigonometry that we have. So remember, we're talking about sines in a circle. We've seen this diagram several times over the last few days, but we're looking at, of course, the half chord, which is equivalent to a particular arc here, and we call that the sine. So in all the demonstrations that we look at, they're all basically looking at the various geometrical relations that we can use and exploit for our purposes in the circle. You'll also notice that I'll be quite careful to use this capital sign here, which is related to the modern or lowercase sign by a scale factor of the radius. You saw the maximum value on our sine table was 60, which is just a scale factor of 60 times our sine of 90, which we're used to seeing as 1 here. So the capital signs are indeed meaningful to refer to the fact that we're dealing with signs with a non-unity radius here. Now, very interestingly enough, and this is one of the rare passages, I don't know of any others, but please bring them up if you know them offhand, is actually why Indian astronomers used the sine and not the chord function that their Greek predecessors had used. We know very little. We know, of course, that they used it, but the actual reason as to why they saw the sine, this half the chord of double the arc, rather than the chord function. I mean, there are reasons we can posit, but it's very rare in the literature we actually see Sanskrit scholars explaining why or what the origins of the sine function was. Nityananda says here. Why do we call this the sine? He says, this is because, and this, all the stuff that's in brackets is my supplied, but I think it's okay with the context. This is because in astronomical models, the position of the planet lying at the tip of the half chord is situated perpendicular to the central line intersecting the chord, is computed using this measure. So this is a little bit of an insight that it may have been thinking about the planetary models more diagrammatically or geometrically, and seeing that, in fact, this half chord is much more useful when you're conceiving of planetary motion than the chord, is the reason into why the sine was originated in India. And they saw it in quite the way they did. So very interesting. So some background to both the terminology and the origin of why they started to use this half chord rather than the chord. So how many sines can one compute? Nityananda then goes on and says, the rationale behind the computation of sines is described in 5 sections. He says, since there are only 30 sines, accurate values are obtained from the sine of 1/3 of 3 degrees. So what he's alluding to here is geometrically, we can find in a quadrant 30 sines only by using these various identities on a circle. Any more, and we have to get a bit more clever about how we get down to the sines below the sine of 3 degrees. So of course, if you do the lowest sine we can find is the sine of 3 degrees geometrically. So the sine of 2 and the sine of 1 degrees, we have to use a little bit more prowess. So this is what Nityananda is referring to here. Of course, his table, as we saw, had 90 entries. So he's alluding to the fact that we're going to have to use a few tricks to get more than the 30 sines, which we can find by pure geometry alone. So the section starts out, and I won't dwell on these. We've had some lovely presentations, especially with the sine of 18 degrees here. You can see there's some familiar diagrams here, and that we see in the manuscript to find the sine of 18 degrees. We see the sine of 45 degrees is epitomized in a manuscript here with the trija, the radius, the kotija here, and so forth and so on. So he gives in the following verses the sine of 90 degrees. These are all very standard and were known very long before Nityananda's time. The sine of 30 degrees, which is half this radius, the sine of 18 degrees, and from this you can find the sines of 72, 54, and 36, and 45. And he gives us not only just the formula for determining these, but also the ways in which we can find them with recourse to these diagrams that we see, which are included in some of the manuscripts. So I won't dwell on those. The other two very important identities that he gives with a good rationale and demonstration for why they are correct, but I won't dwell on these either, are the so-called half-angle formula and the double-angle formula. They look a little nasty, but I've kept them in the way, well, the symbolic equivalent of the way in which Nityananda has expressed them in the text. So we see here, we can, for any angle, we can find half of it, if you like. So this means that if we have the sine of 72 degrees, we can apply the half-angle formula to get 36, and apply it again to get the sine of 18, and apply it again to get the sine of 9, and similarly from the sine of 30 to the sine of 15. So we can fill up many values of our sine table, but we can only get down to the sine of 9 degrees. So what next do we need to do to get at least down to the sine of 3 degrees is what Nityananda tells us next. So this is what I'm going to look at, this rule, which of course is known at least as early as Bhaskaracharya in his Jotpati, but is given quite an interesting rationale and demonstration by Nityananda. So the verse is given, Anyonya koti mavrigunite ye cheshta chapa yodorje. Okay, the sines of two desired arcs, so we imagine these to be, say, theta and phi, are mutually multiplied. Okay, so the sines of sine theta and sine phi are mutually multiplied by the cosines of the other two. So if you multiply sine phi by the cosine of the other one, and whatever is the sum of the two, so adding them together, that is the sine of the sum of the two arcs here. So this is, as I said, an old formula. It's well known by scholars. What is interesting by Nityananda is the way in which he derives this for us. And I'll just compare it, although Professor Ram looked at it in his talk yesterday. is there's of course two identities that are important. You can both take the sum of two arcs, but you can also take the difference. And the verses in Nityananda, it's almost as if he's playing with us very beautifully by the verses. If you read them, Anyonya Kotimarvya, are almost identical, except in the bottom where he uses yogaha, which means sum here, and for the difference he's using viyutihi here. So you've kind of got two verses for the price of one, as long as you know where to put the right word, sum and difference. Very clever poetic skills Nityananda has. So with this is included, with this verse that gives the rule for finding the sign of the sum of two arcs, is this very interesting diagram. Now, if you really went by this, I think the scribe probably was at the limits of his mathematical prowess here, because this is quite difficult to follow, and lines should be perpendicular when they're looking slightly diagonal, but we can reconstruct it based on the evidence. But we really need this diagram to help us understand the following verses in which Nityananda describes the process. Now, the verse that he starts off to demonstrate this is a very lovely one, and something very novel is going on here. I'll just read you a little bit of it. Kakagagam bhumitaleshu mandalam nakendrakam kartakakena sariyet. Now, for those of you that know some Sanskrit will know that kakagagam is a funny-looking word. Okay? And in fact, it is not a word at all, but it is rather the first four letters of the Sanskrit alphabet, the first four consonants of the Sanskrit alphabet. So kakagagam literally means ka, ga, and ga. So these are our lettered points. Bhumitaleshu, on the surface of the earth, mandalam. So may one draw with a compass, a karkatakena, a circle, and you label it with ka, ga, and ga. All right? So we have here in verse, for one of the first instances, how to letter a diagram in the Sanskrit sources. And we put the center to be the corresponding nasal to these gutturals, na. And then we continue by drawing these. And I've just got this up here in a diagram, and so I've got rid of the nagari now. So may one draw a circle, so let's go for it. We draw a circle, and we put on them ka, ga, and ga with a compass, and we label the surface na. And it's the center na here. And he continues. Now we mark two arcs with pairs of letter. Okay, ka and cha. So we understand these arcs. So have in mind your sign diagram here, and then ka, cha here. Then sequentially, may one draw the three radii, okay? Ka, na, cha, na, and cha, na. It's really good for me to practice really pronouncing my alphabet properly. So we have this diagram. So in a verse, he's given us these instructions to draw this lettered diagrams with the quasi sort of half Sanskrit, half mathematical speech in it. And then he continues with the construction, and it gets quite complicated. So I won't read the verse here in the interest of time, but what we do now remember what we are trying to do is show the sign of the sum of two arcs. So if we imagine one of our signs to be with this arc here, ka, cha, all right, so this is the sign here, and our other sign to be cha, cha, which is this perpendicular dropped here on the radius. What we are looking for is the sum of these two arcs, which is this line cha, ta. So that is what we are showing geometrically, okay? So given these two signs here, this whole arc, okay, adding these two together, we want to find what is this length here. So he tells us how to add in various points along the way. So he not only tells us how to draw the diagram, but identifies important bits. So the first sign, okay, the two signs corresponding to the two arcs are dropped as perpendiculars onto the radii ka, na, and cha, na. So here they go, drop this one here and drop this one here, and you'll have yourself two signs. Okay, and we continue on. may, wherever the sign corresponding to the sum of the two arcs, ka, cha, falls on the radius, we mark this point, ta, here. So he's setting up the diagram. May the skillful mathematician draw the line denoted by ja, ta, across here. So these are little bits that he will need in his demonstration, and the point of intersection, we call this here ta. So one of the important things that is crucial for this demonstration, which is not demonstrated until later, is in fact this dotted line here, which is not in the diagram. This in fact is equivalent, and we'll see this later on, to the sign ka, cha, okay? So just remember, we need to show this ta, cha is equal to ka, cha. Okay, now we put our similar triangles to do some fairly serious mathematical work. So he starts identifying various triangles for us. In the big triangle, okay, in the big triangle, cha, ta forms the base, okay, so we can see he's identifying this big triangle here, and ja, ta and ja, cha are the two sides, okay? So the three triangles are clearly identified, and now he proceeds to do his rules of threes on these. I'll just skip past this. So if you like, I'm resisting the urge, of course, to call these angles because, of course, we're really dealing with the arc, but I've identified angles which are equal with black, okay, we can imagine this is phi, if you like, and red, which is theta. So by equivalence, that this triangle here, okay, is similar to this triangle here because they share this red angle in common. And similarly, the other triangle that he will need is the triangle cha, na, cha, is similar to this little triangle here, ja, ta, ta, which he will also use for his trirashika. So he's just telling us that's in the content of the verse there. Now, he's identifying the rules of three. So if we consider, say, our big triangles, cha, na, ja, we can pull out the base, okay, and we can pull out the hypotenuse, okay, the karna or the hypotenuse and the base. So this triangle here with the black angle is similar to this triangle here with the black angle. So he's got these sides here, ja, ta, and ta. Similarly, he expresses another trirashika. This triangle here with the red, na, cha, ja, is similar to cha, ja, ta. Okay, and pulling out, if you just sort of rotate them in your mind, the similar triangles here, if you take the hypotenuses and you take the bases of these, you will get your proportions as well. Now, pulling out a little bit of mathematics on these, with this rule of three, we want to find ta, ta, okay? And ta, ta is just equal to ja, na, times ja, ta, divided by cha, na. Now, each of these themselves are trigonometric amounts. So we see that the side ta, ta in the previous diagram, okay, this amount here is equal to this expression here, okay, cos v sine theta. And similarly with the other red triangles, we can pull out cha, ta. Why do we want to pull out cha, ta? Because it's the other half of this line, the whole of which we're trying to find. And we can find by the rule of three that cha, ta is equal to cos theta sine phi. And of course, adding them together, adding this little bit and this little bit here, we get the length of the entire sign that we were looking for, and in other words, it is shown. So a little bit of dancing around with these triangles here and finding similarities, but what Nityananda has very cleverly and clearly shown by recourse for moving through the diagram, both with respect to constructing it yourself, lettering the points, identifying the triangles, showing the trirashika, he gets to this identity here in a very beautiful way. The demonstration of this equation, there's a little bit of maths in here which isn't completely made explicit by Nityananda until the end. And the reason I'm bringing this out, this one little bit here, that this ja-ta is equal to cha-ja, and working with my colleagues, Professor Raman, Reverend Damaloka, we were really confused by this, why this line here should be equal to cha-ja here. But Nityananda tells us later on, and he tells us by means of a construction, okay? You can show it algebraically. I won't dwell on the details here in the interest of time, but I will rather work through, again, Nityananda tells us in a verse how to perform a construction. You'll see this very interesting, the scribe has really attempted here, and I suspect even using a compass, because these circles are looking quite similar, to actually show the equivalence of these line segments. What he tells us to do is start with our diagram that he'd tell us, kaka, gaga, bhumitale, shumandalam, and we, using the points we've got, we establish this point down here, ga, which he says, using a compass, you form this equilateral triangle and zip out, zip off in either direction that goes through ga-ta and ga-ja, a big long line. Then using these centers, okay, ja, and the radius of the sign, you can draw a circle around here. This is a blue circle. And similarly on the other side, we draw a circle as well. And the 2 points of intersection of these circles on this line here, we call da, all right? So remember, what we're trying to do here is show that cha, ja, and cha, ta are equivalent. So we're getting there with circles. So now we have a length ja, da. Now he tells us, with the ga as the centers and with radius ga, da, you are to do a very big circle, and this is this red dotted one here, and you'll get a point of intersection on this other line that you shot out right at the start, and he calls that da. Then using this radius here, you draw another circle, okay, with the radius equal to ja, cha, which is our original sign, and we can see that in fact the line ta, ja, or as he says, it goes right through it, giving us the length of this. So we have shown by means of a construction, or at least showing the rationale behind this, that the cha, ja, which is so crucial, and ja, ja to the derivation are equal. So it's proven by means of using your compass and showing for yourself, demonstrating for yourself by means of a compass, that in fact these are the same. Okay? This is the slide I should have been using. Okay, so there are 3 circles there to show the equivalence of these 2 lines. Okay, and there it is there. You know, really, if you only had this diagram to do and not Nityananda's instructions, you would be very confused, as the scribe has obviously been quite confused as well. But the construction, of course, is close enough and refers to the original. Okay, so stepping right back, now that we have our new toolbox, we've got all of these sine of 90, sine of 30, sine of 18, sine of 45, we've got these half and double angle formulas, and now we've got these 2 lovely addition and subtraction formulas. We can in fact use these to find our 30 sines that Nityananda was talking about. But remember, we need to get to 90. So how do we get these 30 sines? How do we use the sum and difference? Well, of course, as we saw, from 72 we can go to 36 to 18 to 9, from 30 to 15. But of course, having 9 and 15, we can now use our sums and differences to get the sine of 6. And of course, we can apply the half angle of this to get 3. And of course, once you've got down to the sine of 3, you can just keep doubling it all the way up, and you'll get your 30 sines in a quadrant. Okay, and so that explains, and in fact, if you do the maths very nicely, every third entry of the table can be perfectly computed using these formulas here. However, as we see in the table, we've got more than every 3/3 sine. We've got 1 and 2 as well. So how does Nityananda expect us to find the sine of 1 degree? Once we have the sine of 1 degree, and of course we've got the doubling or the addition formula, we can find any sine that we really want to. Now, of course, it's an outstanding problem or at least it's an outstanding fact, that you cannot find the sine of anything less than 3 degrees geometrically. So Nityananda has to do a little bit of a trick here. Sorry, and we won't dwell too long on what that is. Nityananda alludes to the fact that he says you can approximate the sine of 1 degree by dividing the sine of 3 degrees by 3. Okay, so that might be for people who are in a bit of a hurry, and of course it's not too bad, but if I take this sine of 3 degrees and I divide it by 3, I do not get the number he's got in the table. So Nityananda continues on to tell us how to find this elusive sine of 1 degree we get in the table. And of course we've got a bigger sine table that we find in one of his original works, the Siddhanta Sindhu, which has in the entry not only the sines down to 1 degrees, but the sines down to 1 minute of arc. That means this sine table itself has 54,000 entries. Actually, not only that, it's got double that. As well as having all the entries, it has got all the differences as well between various entries, which you see in red here, just as a bit of a fuzz. And each entry is to 5 significant places, so that we're talking about a table which has around 500,000 numbers written in it altogether. The differences, of course, suggest that Nityananda means you can even interpolate to smaller than arcs of 1 minute. So if we look very closely here at the sine of 1 degree, and again, I'm sorry it's fuzzy because the original rendition I've got, the manuscript is available to look at in Jaipur in the palace. 1, 2, 49, 43, 11, which is precisely the value that we find in this table here. 1, 2, 49, 43, 11. So how did he compute the sine of 1 degree? And I'm just going to leave this as a little bit of a teaser. There are known procedures which do circulate in India, and we also see them in other authors besides, particularly in the Islamic Near East, which use the multi-angle formula here. Okay, this is just applying signs of powers. I'm just slipping from our modern day signs to our signs with an arbitrary radius here. So I've got the capital signs here. So the sine of 3, the multiple of 3 of an arc can be determined here. If you just substitute in theta is equal to 1 degree and let y be sine equal to 1 degree, we have here a rather nice looking equation, which Nityananda then describes how to solve recursively in a very nice way. Of course, what we need to start off with is the sine of 3 degrees. We have this in a table, but Nityananda also gives it in this wonderful verse, which is largely Buddha Sankhya, the sine of 3 degrees to this stunning amount of 1, 2, 3, 4, 5, 6, 7, 8 sexagesimal places here. So very, very accurate, he seems, we were to start off with when we were computing this elusive sine of 1 degrees. And so you can start off with your first approximation. Of course, you can assume that y is small enough, that its cube is even smaller, so we'll just drop that off, and then we can generate subsequent approximations to the sine of 1 degree by just iterating this formula here. Nityananda, in fact, describes 3 different ways in which to compute this recursive algorithm here, and in ways that are slightly different to any earlier ones, particularly those that we see in the Islamic Near East. After some iterations, though, we see that we get the sine of 1 degree to be 1, 2, he gives it 49, 43, 11, 14, 44, 16, 26, 17. Of course, his table only goes to the 11, but that perfectly explains the number for the sine of 1 degree that we see in the table. Now, of course, Nityananda doesn't just compute this, but remember his emphasis on finding the rationale, or at least telling you how he got this, and he gives not only a geometrical demonstration, but a very interesting udaharana, or worked example, where he uses these quasi-symbolic styles of algebra here. We've got yavat, which means literally y squared, if you like, and various things, and quite complicated expressions to, in fact, derive a symbolic expression for the formula to generate the sine of 1 degree right here. But that's just a teaser. That's something we're still working on and will be brought out. So just to conclude, we've looked at now how Nityananda, we found a sine table. We not only found a sine table, but we found a sine table in which an author who was committed to talking about how to compute it and the rationale behind the various computations produces the numerical data that we find in it. That's a very rare example where somebody is so helpful like this, but because it's in a siddhanta, because Nityananda is so committed to producing the reasons behind these numbers are what they are, we can recompute these numbers with certainty and get an idea of what it meant to compute a sine table, at least according to Nityananda. What's really interesting, in particular, is look at the methods of justification and validation in Indian mathematics more generally, is that Nityananda uses a multiple of techniques in his toolbox to justify these signs. He's using quite sophisticated diagrammatic reasoning with these lettered points, which as far as I'm aware is one of the first examples that we have of actually lettering points in the Sanskrit corpus. Please correct me if I'm wrong. We have construction as well, which is sort of a diagrammatic reasoning, but of a sort of a different sense. We have geometrical identities, and we also have symbolic styles of reasoning going on in quite a sophisticated way indeed, which we might loosely call algebra here. There are similarities with the Islamic derivations for the sine of 1 degree, which appeared earlier with scholars who are linked to, or may be in fact, Al-Kashi. An Arabic account was published by Rosenfeld and Hogendijk in 2003. There are many similarities of Nityananda's account with this account, which has been published in this manuscript of unknown authorship by Rosenfeld and Hogendijk. But there are also some very, very significant differences, which shows a way in which Sanskrit scholars were really adjusting this procedure to their own cultural context. Also, very excitingly, although the date I think we're not terribly sure of, is this Jachapa Utpatti, which I'm working on with Professor Pofker and Glenn Van Brummelen in Canada, which shows similar procedures, but with some significant differences as well. So obviously this is the time of the second millennium in which these procedures were being transmitted and explored by various authors. Anyway, all of this is written up more precisely. Of course, I've subjected you to some fairly technical manipulations with diagrams, but just to see the sorts of quality of derivations and justifications that Sanskrit authors can have, but the details you can read more quietly and at your leisure in Skiamus and forthcoming, we hope, next year for the sine of 1 degree. Thank you very much.